Hey everyone, let's jump right into a question that seems super simple. But trust me, the answer is going to completely change how you look at a flickering candle or a roaring campfire. So let's get right to it. What is the state of matter of fire?
You know, back in school, they drill it into us, right? Solid, liquid, gas. The three big states of matter. So naturally, when we look at fire, our brain immediately tries to file it away in one of those categories. It's such a basic, fundamental question about the world.
So what's your first guess? I mean, it's not hard like a rock, not wet like water, so it's got to be a gas, right? That seems logical. Or maybe you're one of those people who've heard whispers about plasma, the fourth state of matter. Well, hold on, because the real answer is way cooler. And it all starts by realizing we might be asking the wrong question entirely.
Okay, so here's the first big mind bender. To get this right, we have to totally shift how we're thinking about it. We've been trying to label fire as a substance, a thing. But what science really tells us is that fire is an event.
So when we see those flames, what are we actually looking at? It's not a thing itself. Fire is just the name we've given to a process called combustion. It's this super fast, super energetic chemical reaction. Think of it like a chain reaction that's just tearing fuel molecules apart and spitting out all that energy we feel as heat and see as light.
And that right there is the whole problem. Asking about the state of matter of fire is, well, it's like asking what's the state of matter of a sunrise or what's the state of matter of digestion. It just doesn't compute, right? Those are processes. They happen to matter, but they aren't matter themselves. It's a classic category error, trying to shove a square peg into a round hole.
Okay, so if fire is a process, are we done here? Is the question just wrong? Well, not exactly. Because even though fire is the name of the reaction, that glowing thing we see, the flame, that part is absolutely full of stuff, real matter that we can actually break down. So let's zoom in and take a look inside the flame.
So what do we find in there? It's actually a wild cocktail of stuff. The vast majority of it is hot gas, just as you'd probably expect. You've got vaporized fuel getting burned up, and then the exhaust, basically like CO2 and water vapor. But, and this is the cool part, it's also got tiny little solid particles floating around in it. We're talking soot and ash. And get this is one of my favorite science facts. That classic yellow-orange color of a campfire, that beautiful glow, it's not coming from the gas. No way. It's coming from those little bits of solid soot. They're basically tiny chunks of carbon that get so incredibly hot that they start to glow, just like the filament in an old light bulb. The solids are what give the fire its color. How cool is that?
Now, even with those solids in there, a flame is still mostly just super hot gas. I mean, its density is ridiculously low, like a fourth of the air around it. And that's exactly why flames always shoot upwards, right? The hot, light stuff rises. And you're going to want to remember that little detail because it has some seriously weird consequences a little later.
All right, so a flame is a mix of hot gas and solid particles. Got it. But I know what some of you are thinking. Wait, I always heard fire was plasma. That's a super common idea, so let's tackle that misconception head on.
First things first, what even is a plasma? It's more than just a really, really hot gas. To get plasma, you have to pump so much energy into a gas that its atoms literally get torn apart. You're left with this soup of positively charged ions and negatively charged electrons. But here's the key. You need a lot of them. Enough so that they stop acting like individual particles and start acting like a group, a collective, that can be controlled by things like magnetic fields.
Yeah, scientists are pretty strict about this. There's basically a 3-point checklist to qualify as a real plasma. You need that group behavior, and the particles have to be dense enough to create this thing called an electrical shield. It's a very specific set of conditions. It's what separates a true plasma from what is basically just a hot gas that happens to have a few charged particles wandering through it.
And it all really comes down to temperature. Think about a candle flame. It's burning around, 1,500 degrees Celsius? That sounds incredibly hot to us, but in the grand scheme of the universe, it's just not hot enough. It can't create that dense soup of ions we need. So, a candle flame fails the plasma test. The proper scientific name for it, a weakly ionized gas. Not quite as catchy, I know.
And you can really see the difference here. A candle flame, that's just a hot gaseous mix. A propane torch gets you a bit hotter, a bit closer. It's a weakly ionized gas. But to actually make the jump to true plasma, you need to get into some serious heat. We're talking acetylene torches or those industrial plasma cutters that are burning at tens of thousands of degrees. That's where you'll find plasma.
All right, are you ready for something really, really wild? To get to the absolute core of what fire is, scientists had to take it somewhere the rules of physics as we know them kind of change. They studied it in space.
Okay, remember what we said earlier about flames being way less dense than air? Well, here on Earth, gravity is always in charge. It pulls down on the heavy, cool air, and that shoves the light, hot gases of the flame upwards. That whole process is called buoyancy, and it's literally the reason flames have that classic teardrop shape. It's also how they get a constant supply of fresh oxygen.
But what happens if you take gravity out of the equation? Suddenly, everything changes. There's no buoyancy, there's no up. The hot gas has nowhere to rise to, so the flame, it becomes a perfect little ball, a sphere. Oxygen can only get to it by slowly diffusing in, which makes for a much slower, cleaner burn. And because it's burning so cleanly, it doesn't create soot. And remember what gives fire its color? Soot. No soot means no yellow-orange glow. Instead, you get these ghostly, dim blue balls of fire. It's absolutely stunning.
So, we've gone through all of this. What's the simple takeaway? Well, the beautiful thing about science is that the answer isn't always simple. The best answer, the most complete answer, actually has a few different layers to it.
So here it is, the complete answer in 3 parts. First, on the most fundamental level, fire is a process, combustion, not a substance. Second, when you look at the stuff inside a flame, it's a mixture of hot gases and solid particles. And third, on that special plasma level, only the absolute hottest, most extreme flames can ever be called a true plasma. If you can remember those 3 levels, you have a really solid, complete understanding of what fire is.
And this isn't just trivia for your next party, you know? Getting this right has huge real-world implications. Understanding how combustion works helps us build way more efficient engines for our cars. And for astronauts, it's literally a matter of life and death. NASA has to know that a fire in space will be a weird, smokeless sphere, so they can design fire safety systems that can actually detect and put it out.
So we started with a simple question and found out the answer was to stop thinking of fire as a thing and start seeing it as an event. It's a process that transforms matter from one form to another. And that kind of makes you wonder, doesn't it? What else do we look at every day and misclassify? Things like lightning, or the sound of music, or even your own shadow. Are they things? Or are they, just like fire, processes in disguise? Something to think about.